Hi everyone, welcome back to the third episode of Decoding Ancient History. That's Decoding Ancient History here on YouTube. Maybe at some point I'll put these videos on Rumble as well. But today we're going to be going over to the great state of Ohio. Ohio in the United States. You can see its beautiful flag there below the U.S. flag. And we're going to be looking at we're going to be using LiDAR data to map the mounds at the Hopewell Mound Complex in Chillicothe, Ohio. So, so Chillicothe is it's about 50 miles south of Columbus, Ohio. You can see Route 70 there going east and west. But Chillicothe there, it's about 50 miles, as you can see the dark blue line there. And in Chillicothe, Ohio, you have, again, what's called the Hopewell Mound Complex. And it's a series of mounds that was built by the Hopewell tradition or the Hopewell culture, which thrive roughly 200 BC to about 500 Common Era. So roughly 2,000 years ago is what we're talking. And today, again, the site is known as the Hopewell Culture National Historical Park. And again, you can see it here on the map. And in this black line that you see there is actually a polygon that I drew. So we're going to be using LiDAR data to map these mounds. And this LiDAR data is downloaded from the U.S. Geological Survey. This black polygon that you see there is an area that I'm using to filter out points that are surrounding forests. So there's some surrounding forests around this mound city, this ancient mound city, and we want to filter out those trees so we're not picking up so much forest. So we'll get to that a little later, but the points of this black polygon are stored in a JSON file. But going back to the overall concepts of the Hopewell site, it was again, it was thriving about 2,000 years ago. It was later mapped in the 1840s by European Americans, and it was excavated by the Ohio Historical Society in the early 1920s. And again, we're going to be using a local-maxima approach, and we're going to be using the Python programming language and various scientific Python packages. So you got GDAL, the Geospatial Data Abstraction Library, scikit-image, matplotlib, and so on and so forth. So before getting to the coding, what I want to emphasize here is the data can be downloaded from the U.S. Geological Survey, and it's LiDAR data. It has a .laz extension, and it contains XYZ points, basically latitudes, longitudes, and elevations. So you can go here. It's the link will be in the description, but it's https://apps.nationalmap.gov/downloader/pound. So this is where you can get the data here. You can go to elevation source, LiDAR, IFSAR. You can select LiDAR point cloud. You can zoom in your area, draw a polygon, and you'll see some LiDAR data files pop up. So that's where I got the data from, and we're going to get to that soon enough. So go in here into Visual Studio Code. What I have here are three Python, they're utility classes, and lidar.py, you might have seen this before from my first video, episode 1. Actually, yes, it was episode 1. We were visualizing the Grave Creek Mound in Moundsville, West Virginia. So we had this LiDAR class in lidar.py. Again, the class is called LiDAR, and you initialize an object with a LiDAR file name, or a file name that contains LiDAR data. It's a .laz extension. That's how you create an object. This is a constructor method. But there's other methods here for reading the projection string, getting the point count, getting the XYZ points as 3 numpy arrays, getting the header, getting the scaling factors, checking if a latitude and longitude is within a particular bounding box, filtering the latitude and longitude points to a polygon, converting the latitudes and longitudes to decimal degrees or WGS 84, so on and so forth. There's another Python file here called plot_utilities.py. This just contains some simple methods for plotting surface data, XYZ data, and so on and so forth. and geospatial utilities, which you can write. This contains various methods for example, taking a set of XYZ points and using GDAL, the Geospatial Data Abstraction Library, to take those XYZ points and regrid to an output GeoTIFF file. We're going to get to all this, but you can see another method here for creating a CSV file, for example, that's going to hold the points, and converting the CSV to a GeoTIFF. We're going to get to all this. I'm trying to keep this video not too long, a reasonable length, but we're going to be starting with these 3 utility files here, and we're gonna build off of it. All of this code is going to be in the GitHub. There's going to be a link to the Decoding Ancient History GitHub's website. So there's going to be 2 links below this video. We're going to have the where I got the data from, the U.S. Geological Survey, this website. There's going to be a link to that, and then there's going to be a link to the GitHub where you can find all this code. So yeah, this looks good, and I'm just going to emphasize again that we are going to have not only the .laz file containing the LiDAR data, but we are going to have a JSON file, which basically is going to contain the coordinates of this black polygon that you see here, and this encloses most of the mounds, and it sort of omits the surrounding woods and forests that you see there on the map. So I'm sure it's a very beautiful park, and one day I would love to go visit. But for now, I can only be an armchair archaeologist and just tinker around and have some fun on my computer, and that's what we're doing today. So let's create a new source file here. We're going to call it, I don't know, map Hopewell mounds.py. I think that's an okay name. We're going to be using the Python 3 interpreter that's built into my system here. So I have Python 3 installed here. It's actually Python 3.8.10. Pretty outdated at this point, but it gets the job done. We're going to import some built-in Python modules, OS. I think that means operating system, but I could be wrong. It might mean something else. Import system. Import JSON. That's going to help us read our JSON file that contains the coordinates that you saw that enclose the mound city. So we're filtering out all those woods and forests again, but we're going to import JSON, and then we're going to import numpy as MP. This actually is not built into Python usually. It might be in later versions of Python, but I actually had to install this with a pip install numpy. So, and then we're going to import the functions from our 3 utility classes that we have, lidar.py. Well, not utility classes, but utility files. Except, well, LiDAR this actually is a class, as I explained earlier, but these other 2 files, plot utilities and geospatial utilities, there's no classes here, it's just functions. So, but let's just import everything that we need from those. So we're going to say from LiDAR, we can import LiDAR, the LiDAR class. We can say here from plot utilities, import star, we're going to import all the functions, and the same goes for geospatial utilities. So from geospatial utilities, and we're going to import everything. We're also going to import some other Python functions that are going to be useful for us from other third-party Python libraries that we talked about earlier. skimage, so from skimage.feature, we're going to import peak local-max. We're going to be using this function later, as we're going to see. Don't worry about it for now, but we're going to get to it. We're going to import the GDAL library. So we got GDAL, and then we're going to import, let's see. Right, we're going to import a Gaussian blurring function. So we'll also get to that later, but usually before you apply a function like peak local max, you want to smooth the image out so there's less noise in the image, and the local maxima algorithm will work a little better. There'll be fewer points, it'll be more accurate. So we're going to import a Gaussian function, or a Gaussian blur, or smoothing function, as sometimes it's called. So we'll say here from skimage.filters, import Gaussian. Okay, Gaussian. I'm sorry, I misspelled that. As with any Python file, I usually have I like to define a main method here, and some boilerplate code beneath. And we're going to call the main method. So let's just see if this works right now. So we're going to do Python 3 map Hopewell mounds.py. And we're not getting any errors. So, and of course we didn't really see any output because we're not really doing anything in this main method yet. One thing I forgot to do is, before the main method, we're going to want to define some constants. So, we'll say that this file is equal to name. This is built in to the Python script, the name itself, which is map Hopewell mounds.py. We're going to have a usage method here. I'm sorry, a usage message. And we can just say here, I don't know, usage at the command line. This is command line usage, so Python 3, this file. And then we're going to pass in the name of the Lidar file, which is a .laz file. Okay? We're going to have a tree height threshold is 670. So this can help us filter out. I think the height is in meters, by the way. I could be wrong. Maybe it's meters above sea level, but I actually don't know. I'll have to look more into that. It might even need to be scaled, but we're going to be doing a local maxima here. We're not really concerned with the units so much, but maybe I can find out what those units are later on and put it in the description. So the next thing that we're going to want to do here is we're going to want to define a local max value to use when we're applying the peak local max function. We're going to want to have a threshold that we're going to be using for the peak local max function. So that'll filter out anything that's less than that height. So we'll say here elevation thresh local max, and we're going to say about 646. That's the number that I came up with earlier before I started recording. So let's go down to our main method here, and we're going to go ahead and define our input file name that contains the Lidar data. We're going to say here Lidar LAZ file name is going to be equal to, and I have the Lidar file, the Lidar data file under data here, and it's actually this thing right here, so I can copy the file name. It's under a folder, a subfolder here called data. So that's where I put it. And so we're going to define that as a string. We can say here data slash, and I can paste in the name of the file. And then we're going to, well, actually, we want this to be a command line argument, right? So we're going to pass this actually as a command line argument. So let me comment this out. So we'll just so I know what the name of the file is, but we'll say here Lidar LAZ file name is equal to it's going to be sys.argv1, so it's going to be the first command line argument. Okay? And of course we can put that in a try except block. I don't know, try except exception as E, and we can print out the usage message, so we can make sure that this script is used properly. We'll print out the usage message and exit if the script is not used properly. Okay, but yeah, so the Lidar file name here that you see .laz, that's going to be passed in as a command line argument here to the Python script. Very basic, straightforward stuff here in terms of software and coding. Next thing that we're going to do here is we're going to pass in the name of the Lidar file into our Lidar class. So we're going to create an instance of this Lidar class in lidar.py. So we're going to say here Lidar object equals Lidar. So we're calling the constructor method, and we're going to say here Lidar LAZ file name. Let's print that out and see how that goes. Lidar object. So we can say here Python 3 map Hopewell mounds.py. Okay, so we got to pass in the name of the LiDAR file, right? So we didn't do that. Let's try that now. And there we go. We get an object there in memory. So at least we know the script is working. All the imports and libraries are working. Let's continue on. The next thing that we're going to want to do here is we're going to want to read in an array of latitudes and longitudes. So this is going to be a n rows by 2 column array of containing the longitudes in the first column and the latitudes in the second column. And then we're going to also want the z values, the elevation values, and we're going to say here that we're going to set that equal to lidar object.xyz to WGS84. So we're basically reading in the x, y, and z values from this LiDAR file, the latitudes and longitudes, and we're converting them to decimal degrees, WGS84 projection, and we're also getting the z values. So we have a method here in lidar.py to do that. It's an instance method, so we're using that. Again, you can check the GitHub account, and if you want to take a closer look at the codes in lidar.py, the class there, be my guest. But that's what we're going on. That's what we're doing right now. We got the latitudes and longitudes in an n rows by 2 column array, and we also have the elevation values. This is a 1 column array with this. It should have the same number of rows as longs lats here. So the next thing that we're going to want to do is we're going to want to read in that polygon that we talked about earlier that encloses the mound city, the Hopewell mound city. So this black polygon that you see here, the vertices of that polygon are stored in a JSON file. So let's go ahead and grab the points of that polygon, and then we're going to use it to filter out the points here that we have, the latitudes, the longitudes, the z values, the elevations. We're going to filter these out, so we're only going to get those points that are within that black polygon that omits the surrounding woods or forest. So what we can do here is we can say here polygon vertices, it's equal to an empty list, and then we're going to say here width open, and then we're going to say here, and I think that the name of the file was it's mounds area coordinates polygon.json. So that's the name of the file. Let's just grab that here. So that's under data as well, the data subdirectory. So I know it's just going to be hard-coded for now, but that's fine for our purposes here. We're going to read the JSON file, and we'll call it fpoints as the file object. So width open, and we're going to say here polygon. We can say here polygon coordinates equals, and it's going to be a tuple. Well, first of all, we're going to say here JSON.loads fpoints, and we're going to grab the coordinates. It's going to be a hash or a dictionary, and we're going to grab the coordinates and the first element there, and then we're going to convert that to a tuple. So what we basically have here is a tuple. Well, let's just print it out and see what it looks like. Polygon coordinates. Let's print that out and see how it looks like. So we can run it at the command line here, the script. And JSON object must be str bytes array. So what do we have here? JSON.loads. I meant to say here JSON.load, not JSON.loads. I think that was incorrect. Fpoints. Let me just double check this. And let's try this one more time. Sometimes you get a little bit of bug when you're doing software development here. Okay, so that we have it now. So what we have here is a tuple where each element in the tuple is a point that defines the enclosing polygon around the Hopewell mounds. So in each point, you got the longitude in decimal degrees, as well as the latitude as the second element, in decimal degrees. So this is a tuple of points, basically, where each point is actually a list, if that makes sense, a Python list. So we're going to be using this later on, these polygon coordinates, and the next thing that we're going to want to do here is we're going to want to filter. We're going to want to use this polygon to filter our latitudes and longitudes to the polygon. So what we can say here next is we can say here lons lats and polygon indices. And we're going to call another method from our Lidar class, and we're going to say Lidar, and this is going to be a static method or class method that we're using here, I think. It is, because we have the name of the class here. We're not using the Lidar object. We're instantiating the class. So we're going to call a class method here, or static method in Lidar. It's going to be called .filter long lats to polygon. All right, and we're going to pass in our lons lats as well as our polygon coordinates that we have up above there. Okay, so let's see how that looks right now. No, we don't need an extra equal sign there. We're just passing in these two things. So yeah, this looks pretty good. So we basically took our longitudes and latitudes that we read from the .laz, the Lidar data file here. We took our latitudes and longitudes as well as the z values, and what we did was we obtained the indices of where these points are inside the polygon. So we actually are going to use these indices. Polygon indices that are returned to filter out our points. So we're only getting points inside of the polygon that encloses the mounds, the mound city, right? So let's use those indices. So we can say here lons equal lons lats colon, so that's all rows, column 0. Lats is going to be lons lats all rows, column 1. Then we also got to filter out our z values. We're going to say z is equal to z polygon indices. Okay? The next thing that we're going to want to do here is we're going to want to remove any points that are probably corresponding to trees, right? So I'd like to assume that this whole area, and I guess this is just an assumption, that this area, this Hopewell Mounds complex, is relatively flat. So the surrounding trees and even some of the trees inside the park are much taller than the mounds themselves, although I could be wrong about that. But I'm going to go ahead and do some filtering anyway, and try to filter out trees inside the image. So we can say here, non-tree indices is equal to numpy.where z is going to be less than our tree height threshold that we define above. So the tree height threshold we defined as a constant up here, 670. And let's go ahead and use that. So yeah, this should get our indices where we do not have trees. So hopefully we just have the mounds. So let's see. The next thing that we're going to want to do here is apply that filter. So we can say here the lons is going to be equal to lons, non-tree indices, lats equals lats, non-tree indices, and finally z is equal to z, non-tree indices. Okay? And so now that we've done some filtering, we filtered these Lidar points from our Lidar data file, the .laz file that you see here. After we've done two sets of filtering, we filtered so we only have the points that are inside of this black polygon that you see, and we also hopefully filtered out any trees that were inside the within the data itself by using a simple threshold. So this is where the rubber meets the road. The next thing that we're going to do here is let's just visualize the mounds. So we can say here, let's just see what the data looks like right now. So we can say here, outname PNG is equal to, I don't know, outputs, Hopewell, Mounds, video.png. And we can go ahead and visualize those mounds. We have a method here in plot utilities called visualize mounds. That's actually being carried over from our first video when we were talking about the Grave Creek Mound. The very first video in this YouTube series, we were visualizing the Grave Creek Mound in Moundsville, West Virginia, but we had this method visualize mounds, which calls this plot trisurf method to make a very pretty visualization of that. So let's just call that. So we're going to call that method. So we're going to call visualize mounds, and we're going to pass in the longitudes, the latitudes, the z values, the elevations, as well as the outname PNG. Let's run it. So it might take a little bit to run. Hopefully we get a new file in our outputs folder. It should be called Hopewell Mounds video.png. I have some other files here from previous testing, but I gave it a new name. Let's see. It might take a second to run. It's actually taking a little bit longer to run than I thought it would. Let's try to be patient here. I kind of have an old computer. This is from 2018. It's an Asus ZenBook. It's top of the line when I got it, but its age is starting to show. Okay, so we're done, and what do we have here? Hopewell Mounds video.png, and there we go. We can see the mounds there. We can zoom in there, and that looks pretty good. This is what we would expect the mound city to look like. So that looks really good. Cool. All right, so let's move on then. The next thing that we're going to want to do here, so now that we know that the data looks reasonably good, the next thing that we're going to want to do is take our filtered XYZ points, our LiDAR points, and we're going to want to dump it to a CSV file. A CSV. It's a comma-separated variable. So we can say here CSV file name is going to be equal to outputs. I'll just call it dem.csv, digital elevation model.csv. I like to use dem. It's a nice name. Pretty fancy. Well, not really, but okay, so let's take the points and dump it to a CSV. And like I said earlier, we're going to be taking that CSV and we're going to be using the GDAL _grid utility. It's a command line utility to take that CSV and convert it into a regridded geotiff. So we're going to get to that very soon. So we're going to want to say here, we can call a method XYZ to CSV, which is in our geospatial utilities file, geospatialutilities.py. And I think it's at the bottom here. Yeah, here it is, XYZ to CSV, right? And so we can pass in our longitudes, the latitudes, the z values, elevation, as well as our CSV file name. Okay? And I think that should work fine. The next thing that we're going to want to do is when this CSV is dumped out, when outputs dem.csv, I'll call it demvideo.csv just to make it a new unique name. But when this CSV is dumped out, the next thing that we're going to want to do is convert it into a geotiff. So we're going to call our CSV to geotiff method. We're going to pass in our CSV file name, and we also need an output name for our geotiff. So I'm going to say here outname tiff is equal to outputs Hopewell, I don't know, mounds video.tiff. All right, there we go. Lovely. And outname tiff. So let's pass that in. And let's go ahead and give the code another run again. Make sure everything is on the up and up. Okay? So we're running the code again. And as we saw earlier, it's going to take a little bit of time. Let it run, and let's just see if we get our output files as we might expect. We should get a CSV file, .csv, right here. And we should also get a GeoTIFF file. And if we do get the GeoTIFF file, we're gonna dump it into QGIS and see how it looks. I want to see how it looks. Maybe at some point I'll develop my YouTube editing skills to filter out these waiting times, because... Okay, so unable to find... We got an error here. So dem video.csv, so... Well, our CSV file looks okay. So we got an error here. So what is going on here? Unable to find layer DEM. Oh, okay. I think that I think I messed something up here. Whereas when we run the GDAL _ grid utility, it has to have a certain name, the CSV file, because we're creating a virtual file here. So if we go to geospatial utilities and yeah, I think we just have to give it the name dem.csv. So that's my mistake. So you know what? We're just going to call this. Let's just call it dem.csv, and we'll just dump it out to the current directory. Both of these files. So we have dem.csv and Hopewell Mounds _ video.tiff. So let's try this one more time. Again, I'm sorry, that was a bug on my part. So basically, the GDAL grid command line tool that you see here, the GDAL grid, when we use that, we're basically passing in this .vrt file, this virtual file that's also written out, and it has the name of the CSV file has to have the same name that's here, dem. So they got to match there in order for this command line tool to work. So it's from GDAL, the Geospatial Data Abstraction Library. Very powerful. Hopefully it'll work this time, and we'll get a GeoTIFF file in our current directory, not in outputs. So we're going to wait a little bit of time here. Come on. Okay, good, and it ran without error, thank goodness. And I do believe that we should have gotten a GeoTIFF file, Hopewell Mounds video.tiff. So let's go back to our file system. Let's open up QGIS here. I don't need this. I don't know why it's giving me this pop-up, but let's open up QGIS and let's just see how it looks real quick. So Hopewell Mounds video.tiff, and there you have it. You can see here. This is a GeoTIFF file, and you can see here the mounds clearly. It's basically a grayscale image that's being rendered here. You even have a rectangular mound here that you see, sort of rectangular shape, but the rest of these are fairly circular. So what we're going to be doing is we're going to be taking the data in this GeoTIFF, this regridded data. So this GeoTIFF again was created using Lidar data that was regridded to make this GeoTIFF. We're going to be applying the peak local max algorithm to this GeoTIFF data to try to map these mounds and dump the output out as a shapefile, a point shapefile. So let's get back into Visual Studio again, and let me just have a sip of coffee here before I lose my voice. Okay, so now that we have the GeoTIFF, we have a GeoTIFF file containing our regridded data as a 2D array. The next thing that we're going to want to do here is we're going to open up that GeoTIFF as a data set. So we can say here ds-tiff. We're going to say here gdal.open. And we're going to open up outname tiff. All right. Next thing we're going to want to read the band from that GeoTIFF file. It's as a 2D array, a numpy array. So what we're going to want to do here is we're going to say here GeoTIFF band ds-tiff.get raster band 1 .read as array. Next thing that we're going to do is we're going to apply a Gaussian smoothing to the imagery. We're going to smoothen the imagery out. So when we apply the peak local max function, there'll be less noise. And hopefully we'll get better results, and we're not going to get too many false positives, if you will. So we're going to say here blurred is equal to Gaussian, the function that we imported from skimage.filters. We're going to say here Gaussian, and then we're going to pass in our GeoTIFF band. The number of sigmas that we're going to use, we'll just say 2. I think that's an okay value here. And preserve range, yep, and we're going to say here that we're going to set that equal to true. So just defining some other arguments here. And let's go ahead and see what that looks like. So we're going to call another function here from plotutilities.py. It's called plot2d bird's eye. So we're going to basically get a bird's eye view of this quote-unquote blurred or Gaussian smoothed LiDAR data, this GeoTIFF. So what we can do here is we're going to say here plot 2D bird's eye blurred. We're going to say here we're going to call the file, I don't know, blurred mounds video.png, I guess. All right. And let's just see what that looks like. So let's run the script again. And I apologize, there's a bit of a wait here. So huzzah for my YouTube skills and video editing skills, or I should say, or lack thereof. So if this works, we should get another file here called blurred_mounds_video.png, and we're going to see how it looks. Hopefully it'll look pretty similar to the result that we see here, the original GeoTIFF in QGIS. It shouldn't look too much different, other than I suppose it's going to be a little more smoother, so to speak. Less noise, maybe it'll be a smaller resolution, I don't know. But we're just going to dump the result here as a PNG. Okay, so what does it say here? We got another error here. Unexpected keyword argument sigmas, and I know why that happened, because it's actually just supposed to be sigma, not sigmas. Let me run it one more time. Good times, right? Crazy times we live in. Just got a new AC system installed in my house yesterday. That was about $7,000, more than 7,000, $7,600. The guy who came who did it though was he was really nice, and I think he gave me a good price compared to some other companies nearby. They wanted almost 10 grand out of me. Not gonna happen. As they say though, you know, either you do it yourself or you pay the piper. You know, I do a lot of work on my car. It's a 2007 Ford Mustang, and at least I try to do most of the work on that. Although I did have to pay a mechanic to rebuild the transmission, because rebuilding a transmission is way above my pay grade. Even though someday I hope to learn how to do it. Anyways, I digress. Let's. Oh yeah. So the code ran without error, and what we have here, we should have a new file here called blurredmoundsvideo.py, and I think we do. Let's see here. Here it is. Blurred mounds video.py. By the way, I'm using the Linux Mint operating system. It's very good for software development. Let's take a look at let's see what this looks like. So, yep, this is our blurred image of the Hopewell Mound City. And, yeah, it looks pretty similar to the original GeoTIFF where it's derived from. It's kind of flipped upside down here because this is just a PNG. But the point is, you can see it's pretty smoothened out here. So, pardon me. This should, after applying the smoothing, it should make our process of using the peak local max function much smoother. Pun intended, again. Fun stuff, right? So now that we've applied a Gaussian blurring to the LiDAR data that's stored in our GeoTIFF, the next thing we're going to want to do is call the peak local max function. So, again, the peak local max function is from the skimage.feature. So we imported it up here. So let's go ahead and do that. So we're going to say here rows or row column max, I don't know, coordinates. I guess these are the indices equals peak local max. We're going to pass in our blurred 2D numpy array. We're going to also pass in a threshold. And then we're going to use the threshold that we defined above. Elevation local max. Alright, so we define that. Oh. Yeah, we define this threshold at the top there. And, why is this thing... I'm trying to get this split onto a new line, and it's kind of being a pain. Okay, that looks a little better. But yeah, we define this constant up here, elevation local max, 646, that's the value. And this is basically, when we apply the peak local max function up here from skimage.feature, we're going to want a threshold that, so basically this function is not going to include anything below that threshold when it's looking for local maxima. All right, so we got to use that threshold here, down below here. So we got row column max coordinates. Those are indices, and we're gonna want to. And so, what's important to note here is that this peak local max function is going to be returning the row and column indices in blurred, our 2D numpy array. It's going to be returning row and column indices. So if we're going to want to write the results out as a shapefile, like a point shapefile that maps the mounds, we're going to need to take those rows and columns, those y and x values, and we're going to want to convert them into latitudes and longitudes. Okay? So how are we going to do that? We're going to call another method from our geospatial utilities, and it's called rows columns to map coordinates. So I think it's somewhere up here. Here it is, rows columns to map coordinates. So you basically pass in the name of a GeoTIFF. We have a GeoTIFF that we created, and n rows by 2 column numpy array containing your rows and columns. And basically this function uses the it uses a transform method from raster.io. Raster.io is another Python library, and it's going to be using a transform method, if you will, raster.io.transform to basically take those row and column indices and dump out longitudes and latitudes. All right. And then finally, we can take those latitudes and longitudes and dump it out to a shapefile. Okay? And then we can take our lovely little shapefile and write it out and see what it looks like in QGIS. All right? Good times. So, yeah, let's go ahead and try to use that method. So, we're going to say here, longitude, latitude, max, coordinates, it's going to be equal to rows columns to map coordinates, the function I just showed you. We're going to pass in our GeoTIFF file name, And what was that again? Outname TIFF, outname underscore TIFF. So outname underscore TIFF, and then our row, column, max coordinates. We're gonna pass that in too. So we're yeah. So let's go ahead and try to run this. I'm gonna print it out. Long lat. Max coordinates. Let's just print it out and see if that works. And we're almost done here, but let's just try to run that and see if we get some output there, and hopefully it'll run without an error. This is good times. Yeah, I don't know how long this video has been going. Probably at least a half an hour at this point. But I hope to wrap it up soon. I'm going to try to keep these videos under an hour. All of them, at least. I'm going to hope to try to do that, but we'll see how this goes. Yep, we got our code running. All seems well. Okay, good. So it looks like it ran, and we hopefully got some longitudes. So the longitudes is the first column, and the latitudes. We got some longitudes and latitudes that define the locations of our mounds, right? The point locations of our mounds, the top of the mounds, hopefully, but of course the function is never perfect. So one thing I failed to mention here was that this function, rows, columns, and map coordinates, it returns a numpy array, n rows by 2 column numpy array, and the first column is going to be the longitudes, the second column is going to be the latitudes. So finally wrapping up here, what we can do here is we're going to write out the points to a shapefile, and we can do that because in geospatial utilities we have a function here called write points shapefile, write underscore pnts underscore shp file, write point shapefile right here. We pass in the out name, an output file name for the shapefile, as well as our n rows by 2 column numpy array with the x and y coordinates, the longitude and latitude coordinates. And we can write the points out to a shapefile. So let's go ahead and do that and wrap up. So we can see a write point shapefile, and we'll just call it, I don't know, Mounds, locations, Hopewell, video. I hope it worked. Dot shape. Okay, no, that's kind of a long name, but we'll just call it Mound Locations Hopewell Video dot shape, right? That's a simple name. A little bit long, but it doesn't matter. And we're gonna pass in our we're gonna pass in our long lat max coordinates. All right, and so hopefully we're going to get a shapefile that maps our mounds in the Hopewell Mound City Complex. They're in Chillicothe, Ohio. All right, great state of Ohio, beautiful place. So let's try to run this code again. Let me clear the console and give it another run. Enter. And we're getting a little bit of a warning here. The Qt5 CT plugin. I'm actually not sure what that is, but I don't really care at this point. So if this runs to success, we should get a shapefile here. In addition to the shapefile, the .shp file, we should get other files too, like a dbf, a .prga file, and I think a shx file. When you have a shapefile, you usually have these other auxiliary files that go with it. And I do believe my method here writes those out as well. It certainly dumps out the projection file that we have some coded. We have the code that you see right there. But all of this is going to be in the GitHub for this YouTube channel. It's going to be linked below the video. So Well, it looks like it got done running, and if I look here on the left in Visual Studio, I think we got our shapefile. Okay. Mounds underscore locations Hopewell underscore video dot shape. So let's pop open QGIS here, and let's see what it looks like. I can just drag it in. It's a shapefile. And actually, this doesn't look too bad. So it's kind of hard to see, but the points that were mapped here are these little pink dots that you see. So we had the GeoTIFF open from earlier, and we had the shapefile here mapping the mounds. I don't know. There is some false positive you can see here on the side. I don't know what this is. Maybe some kind of... This is like the edge of the image, the edge of our polygon enclosure, so it picked up some false positives there. I think there's a rectangular shape mound in Hopewell, in the Hopewell complex, where it basically, it counted it as 3 points. So I don't know if you want to call that an error. I guess it is an error, but I think this isn't bad for a first pass. It's kind of fun, you know, and one of the reasons I did this was I think that using algorithms like the local-maxima and Gaussian smoothing and all these types of functions and utilities, I think it'd be very useful to apply to in many different contexts, even for an archaeological sense. You know, the point of this YouTube channel is we're trying to use just modern data, open source data, and we're trying to take that open source data and have some fun with it, apply some programming using different programming languages like Python and C++ to try to visualize that data, see what else we can learn from that data, and maybe discover new things, and just have some fun. And that's why I'm doing this YouTube series. I want to see what I can learn and maybe even discover something new. Probably not, but either way, it certainly is fun. So yeah, that concludes the third video of Decoding Ancient History. I thank you for watching this. Again, I thank you for your time. And there's going to be links again below the video to where I got the LiDAR data from the U.S. Geological Survey, as well as the GitHub account for this YouTube channel. So, again, yeah, so we mapped the we mapped the mounds in the Hopewell city group in Ohio, Chillicothe, Ohio, and we'll see what else we can do with the local maxima and local minima functions, similar things like that, maybe in a future video. But for now, I'm going to close this out. Thanks everyone for watching, and I'll